Hello students, good time to all. I am Chandan Kwan Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss basics about electrostatic potential. Let's begin. In order to explain electric potential, first we discuss potential difference. Potential difference, the electric potential difference between 2 points. Since we consider difference, so you take 2 points, electric potential difference between 2 points in electric field. Is defined as the amount of work done in moving a unit positive charge which is also known as the test charge from one point to another, from one point to another against that electrostatic force, against that electrostatic force. And the potential difference between 2 points in an electric field is defined as the amount of work is done in moving a unit positive charge from one point to another against that of electrostatic force. Let me take the electric potential at 2 points. One point is A, another point B. Let the electric potential at point A be VA and potential at point B be VB, and these 2 points are in the electrostatic force E, electric field E, that is the electric field. So here we mentioned VA is the electric potential at point A, VB electric potential at point B, E vector that is the electric field, within that electric field E we consider 2 points A and B, where at point A the potential will be VA and point B the potential will be VB, and we have to calculate WAB, that is the work done, in moving the charge Q naught, in moving a charge Q naught, that is the unit positive charge which is known as the test charge also, from point A to B, from point A to B. Then the potential difference according to our definition, that is the work done per unit test charge. The potential difference, that is VB minus VA, the potential difference is equal to WAB minus divided by Q naught. That is the potential difference between these 2 points. These two are arranged, the points are like B point and A point in such electric field line. So here at potential VB, here at potential VA, the potential difference will be VB minus VA, that is work done in moving a charge Q naught from A point to B point divided by Q naught. That is the potential difference between 2 points when these 2 points are lie in that of electrostatic field. Now we have to take the relation between the potential difference and the line integral of electric field. Relation between potential difference and line integral of electric field. Line integral of electric field, the relation between these two. How we have to relate these two? Let us move a test charge. We have to take 2 points. Here we take the charge Q, which is stationary at point O, and consider an electric field E. In that of electric field, we have 2 points. One is point B, another one is point A. And the potential at point B be VB and potential at point A be VA. So the force acting on the test charge Q naught at point P, here we take the point P, due to the charge Q, means we have to move that test charge from point A to point B in order to calculate the potential difference between these 2 points. So in between these 2 points I take a point P, and here the force acting on the test charge, here will be the test charge Q naught, due to that point P to the charge Q is given as the force on the test charge will be how much. Right here, force acting on test charge Q naught at point P due to charge Q is given by that force F is equal to Q naught into E, E be the electric field. Inside that of electric field we take the charge and the points having the potentials VB and VA. Here the force required to move that test charge Q naught in the opposite direction by an external agency will be just its negative. So, we write the force required to move the test charge Q naught in opposite direction by an external agency will be, the force is just its negative, that is minus Q naught E. That amount of force is needed. Here we take the work done in moving the test charge Q naught from point P to a point Q. The distance between P Q, let that dl be the small distance. So, here the small work will be done and that small work, that is dw. dw amount of work is done when the test charge Q naught from P to Q for a small distance dl. Now, the work done in moving the test charge, work done in moving the test charge Q naught from the point from P to Q through a small distance dl is, that is dw f dot dl, f minus Q naught E vector is equal to minus Q naught E vector dot dl vector. Then the total work done in moving the test charge Q naught from the point A to the point B is given as we have to integrate that work done. Now, the total work done in moving the test charge Q naught from point A to B is given by, that is WAB, which is equal to small work done dw from the point A to B, from the point A to B. So, here from point A to B we have to integrate minus Q naught E vector dot dl vector, minus Q naught to that of outside, integration from A to B E vector dot dl vector. Therefore, WAB divided by Q naught is equal to integration over A to B negative E dot dl. Look at here, from the definition of potential difference between the 2 points, we get Vb minus Va is equal to Wab by Q naught. Now comparing these two equations, here be the equation number 1 and here be the equation number 2, that is the potential difference between the 2 points A and B. Here also the potential difference between the 2 points A and B. So the right hand sides, its left hand side be the same. From equation 1 and 2, from equation 1 and 2, we get Vb minus Va is equal to negative integration over A to B E dot dl, which is also equal to Wab by Q naught. That is the relation between potential difference as the line integral of electric field. Potential difference Vb minus Va is the potential difference is the line integral of electric field E dot dl, line integral of electric field. By using that concept, we can easily derive the electric potential due to a point charge. We proceed towards the concept of electric potential by using the basics of potential difference between these 2 points. Here electric potential due to a point charge can be calculated as the electric potential at a point in the electric field is defined as the amount of work done in moving a unit positive charge from infinity to that point against the electrostatic force. How much amount of work is done when we have to move that unit test charge from infinity to that point due to that point charge. Here look at that figure, this is the point charge, let the charge will be q, but in this case we take that unit test charge from infinity to the point B, means the potential at point A is at infinity, the potential at A will be 0. So here let us choose that point A at infinity, means the potential at point A, potential at infinity will be 0 here. Now putting this in the equation, that equation number 3, we have the potential at that point B. Putting this value, in equation 3, we get work done to take the test charge from infinity to the point B, that is infinity B divided by Q naught is equal to Vb minus Va. So, Vb minus Va 0, or we have Vb is equal to Q infinity B divided by Q naught. That value will be negative of integration from infinity to that point B, line integration of that electric field E dot dl. So, here Vb that is minus integration over minus infinity to point B E dot dl, which is equal to W infinity B divided by Q naught. That is the required expression. Means due to a point charge, we can calculate the electric field when that point charge is situated at that point B. So, the electric potential due to that point charge is calculated in this way. So, if we take, note that, look here, by using that relation we have to calculate potential at point P, potential at point P due to a point charge Q, due to a point charge Q is given by, that is potential at point P due to that point charge Q is given as 1 by 4 pi epsilon naught Q divided by R. This is the potential due to a point charge at point P, as you take that point P here. Now, we derive a relation between electric field as the gradient of electric potential, electric field as the gradient of electric potential, relation between electric field and potential. So, here the potential at point P due to that point charge small q is given by V is equal to 1 by 4 pi epsilon naught Q by R. So, you have V is equal to 1 by 4 pi epsilon naught Q divided by R, that is the potential at point P due to a point charge Q, where R is the distance, here R, that is the distance of point P from charge Q. Let we take the charge Q, here is the point at P, the distance between Q and point P, here is the point at O, here is the point at P, the distance between O and P will be R. At that point we have to calculate the electric potential due to that charge Q, that is the relation. Now, we have to calculate the gradient of electric potential, the gradient of electric potential is grad V, that is grad potential 1 by 4 pi epsilon naught Q divided by R, or gradient of that potential grad V Q divided by 4 pi epsilon naught gradient of 1 by R. Grad of 1 by R can be calculated by using the relation, as we know, since gradient of 1 by R to the power n r be the position vector, gradient of 1 by r to the power n is equal to n r vector divided by r to the power n plus 2. That is the relation. By using that relation, we can easily calculate the gradient of 1 by r. So, here n is equal to 1. So, we have to put that value, that is q by 4 pi epsilon naught. In place of n we substitute 1, that value will be r vector divided by r to the power 1 plus 2, that is the negative, this is the negative, minus n r vector divided by r to the power n plus 2, that is the relation. Here is the negative. That is negative q divided by 4 pi epsilon naught r vector, that is magnitude and its direction, r be the magnitude, r cap its direction, divided by r q. 1 r cancel out, it will be minus 1 by 4 pi epsilon naught q by r square into r cap, that is the value of gradient of that potential. Now, let I prefer it as equation number 1. Now, the electric field, we know that electric field intensity at point P due to charge q, is, if here we calculate the electric field intensity due to charge q, then the relation is given as E is equal to 1 by 4 pi epsilon naught q by r square into r cap. Equation number 2. Comparing 1 and 2, we get that electric field intensity is the negative of potential gradient, grad V. E is equal to negative of grad V. So, here we write electric field intensity at any point, electric field intensity at any point is equal to negative gradient of electric potential at that point, electric potential at that point. So, E is equal to negative of potential gradient. Now, by using the concept of potential difference, we termed a new concept, that is equipotential surfaces. Equipotential means the potential will be same throughout the entire surfaces. A surface which has same potential are at every point is called the equipotential surfaces. Some properties of equipotential surfaces: no work is done in moving a test charge on an equipotential surfaces. If we move a test charge from an equipotential surface, there will be no work done. As we know from that of relation, the potential difference between 2 points, if we calculate, that is VB minus VA, which is equal to WAB divided by Q naught test charge. Since we consider equipotential surfaces, so the potential at every points on that of equipotential surface will be the same. So, the difference between VB minus VA will be 0 is equal to WAB divided by Q naught, as VB is equal to VA is equal to 0, not 0, that is the same, VB is equal to VA. Therefore, the work done WAB Q naught into 0, that is 0. So, no work is done in moving a test charge on an equipotential surface. Second property, the electric field is always right angle to that of equipotential surfaces. Let we take the equipotential surfaces. Here be the point having the charge let Q. These are the surfaces where each points have the equal potentials, and this is the line of electric field intensity, and the direction of that equipotential surface will be the tangent to that of surfaces. So, the direction between electric field is always perpendicular to that of equipotential surface. Imagine it in case of a 3D, means a spherical one of that surfaces. So, the electric field vectors are radially outwards, and the surface direction of that surface is tangent to that of line. So, the electric field and the direction of that of equipotential surface will be right angle to each other. Next property, equipotential surfaces help to distinguish regions of strong electric field from those of weak electric field. Which electric fields are strong as comparison to that of weak electric field, that can be easily distinguished by using that equipotential surfaces. As you know, electric field is the negative of potential gradient, that is dV by dr is equal to negative of potential gradient dV by dr. From these expressions we clear that dr is inversely proportional to that of dE. Change in displacement or change in distance is inversely proportional to the change in that electric field potential, whereas dr is the spacing between equipotential surfaces. Dr is the spacing between equipotential surfaces. So, in order to use that relation, we can say the spacing between that equipotential surfaces in the strong electric field is less, and vice versa. For weak electric field it will be more. So, here by using equipotential surface we can easily distinguish the regions of strong electric field and the regions of weak electric field. Next property, equipotential surfaces tell us about the direction of electric field. How? Since E is equal to minus dV by dr. So, here the negative sign shows that the direction of electric field is that in which the potential decreases, that particular negative sign indicates from that mathematical expression. In order to use that particular mathematical expression, we can conclude the equipotential surfaces tells with the direction of that electric field. Next one, no equipotential surfaces can intersect each other. These are the equipotential surfaces. The two equipotential surfaces can't intersect each other. If two equipotential surfaces are intersect with each other, means the potential, these points are different. Two equipotential surfaces intersect each other, then at the point of intersection there will be the two values of electric potential, but actually that is not possible. That is why the two equipotential surfaces can't intersect each other. This is the basics of equipotential surfaces and some properties regarding equipotential surfaces. So, with the help of this video lecture, we understand potential difference, relation between potential difference and line integral of electric field. Here is that one, and electric potential due to a point charge, electric potential due to a point charge, and electric field as the gradient of electric potential. Electric field is the negative of potential gradient, and the concept of equipotential surfaces and its properties. So, with this useful and informative notes, let me wind up this session. Thank you.